Hey everyone, welcome. Today we're going to tackle something super powerful in AI, something you've actually been doing for years without even realizing it. We're talking about constraint satisfaction problems, or CSPs. You know, if you've ever done a Sudoku puzzle, you've basically used the core logic of a CSP. So what we're going to do is take that intuitive puzzle-solving skill, formalize it, and turn it into an awesome tool for AI. Let's dive in.
All right, so here's the plan. First, we'll break down what these constraint problems actually are. Then, we'll build our own basic solver using a technique called backtracking. But, we're not just going to stop at basic. The really cool part is where we upgrade that solver, make it way smarter, and then wrap everything up with some key tips to make sure you're totally prepped for any exams. Sound good? Okay, first things first. What in the world is a constraint problem? Well, we're about to connect something you do all the time, like solving puzzles, to a really structured way of thinking that AI uses to handle some seriously complex stuff. Yeah, I'm pretty sure you've all seen this before. Sudoku. It's not just a fun brain teaser. It's the perfect example of a CSP. See, with a Sudoku, you're not trying to find the best path or the shortest route. Nope. The whole goal is just to find a final state, a finished grid that follows all the rules. It's all about finding a valid configuration, and that's the key. It could be numbers in a grid, or it could be something way more complex like scheduling flights at an airport.
And that leads us right to the official definition. At its core, a constraint satisfaction problem is just, it's any problem where your goal is to find a solution that satisfies a whole bunch of strict rules, or what we call constraints. It's not about optimization, it's about validity. Simple as that. Does the solution work? Yes or no?
So here's the cool part. No matter how complicated a CSP gets, it always breaks down into just three things. Think of it like a recipe. First, you've got your variables. These are the unknowns, right? The empty boxes in Sudoku, or maybe the university courses you need to schedule. Next, you have the domains. This is just the list of possible options for each variable. For Sudoku, that's easy, the numbers 1 through 9. For course scheduling, it might be all the available classrooms. And finally, the most important part, the constraints. These are the rules of the game. Things like no repeating numbers in a row, or you can't schedule 2 classes in the same room at the same time. Variables, domains, constraints. That's the whole shebang.
This simple 3-part structure is like a magic formula. You can use it to model all sorts of problems as a CSP. And to show you how it works, we're going to use a classic AI example for the rest of our time here, map coloring. The process is always the same. Step 1, figure out your variables. Step 2, define the possible values, the domain. And step 3, lay out all the rules, the constraints.
Okay, check this out. On the left, you see our problem. We've got a map of Australia, and our job is to color it so that no 2 states that touch have the same color. Easy enough, right? So let's use our 3-step recipe. What are the variables? Well, they're the states themselves, Western Australia, Queensland, and so on. What's the domain? It's our palette of colors. Let's say we have red, green, and blue. And the constraints? Super simple. If 2 states share a border, they can't have the same color. Now look at the right. We can turn that map into this abstract constraint graph. Each state becomes a dot, or a node, and we draw a line between any 2 states that touch. That line just means, hey, there's a rule between these 2.
So we know how to set up the problem. The big question now is, how do we actually solve it? We're going to start with the most basic fundamental algorithm out there for CSPs. It's called backtracking search. Think of it as our starting point. It gets the job done, but, let's just say it's a little clumsy.
At its heart, backtracking is just a depth-first search. It's kind of like blindly walking through a maze. You pick a variable, say Western Australia, and give it a value. Let's make it red. Cool. Then you move to the next one, Northern Territory, and make it green. Still good. But then you get to South Australia, and you try to color it red? Uh-oh. Instant problem. South Australia touches Western Australia, so they can't both be red. You've hit a dead end. So what does the algorithm do? It backtracks. It goes back to the last choice it made and tries something different. It just keeps doing this, plowing ahead, hitting a wall, backing up, trying again, until it finally stumbles upon a solution that works for everything.
Now look, this whole try and fail approach, it will find a solution eventually, if one exists. But imagine a really complex problem. This brute force method could take, forever. It's just not smart. Which brings us to the most important question we're going to ask today. How can we make this thing smarter? All right, time for our first big upgrade. Instead of just picking variables at random, what if we were more strategic about the order we choose them in? We can use something called heuristics, basically smart rules of thumb to guide our choices. The whole idea is to find the solution, or realize there isn't one, way faster.
The first, and probably the most important heuristic, is called minimum remaining values, or MRV. The logic is actually super intuitive. Always pick the variable that has the fewest legal moves left. We call this the fail-first principle. Think about it. If a part of the puzzle is about to become impossible, you want to know that right now, not after another 1,000 steps. By tackling the tightest spots first, you either solve the hardest part of the problem, or you find a failure early, which saves a massive amount of time. Okay, but what if you have a tie? Let's say two variables both have only two options left. Which one do you pick? That's where our tiebreaker comes in, the degree heuristic. It's simple. Pick the variable that affects the most other variables, the one that's the most connected in our constraint graph. The thinking here is that picking a value for this variable will have the biggest ripple effect across the whole puzzle, helping you lock things down or find a failure much more quickly.
So, let's just recap that real quick. Your main strategy is MRV. Always go for the variable with the fewest choices left. It helps shrink the problem fast. If you get a tie, you pull out the degree heuristic. Pick the one that's most connected to other variables. Using these two together, it's so much smarter than just guessing.
Okay, picking variables smarter is a huge win, but we can do even better. Our next upgrade is all about seeing failure before it happens. We want to spot dead ends from a mile away. We can do this with some cool techniques called filtering or pruning.
The most straightforward way to do this is with something called forward checking. It's a really clever, simple look-ahead move. As soon as you assign a value to a variable, bam, you immediately look at all its neighbors and delete that value from their list of possibilities. You're actively cleaning up the problem as you go, getting rid of options that you know are now impossible.
Let's actually watch this happen. Keep an eye on the possible colors for each state. Okay, we assign red to Western Australia. See that? The red option just disappeared for its neighbors, Northern Territory and South Australia. Now, let's assign green to the Northern Territory. And poof, green is gone as an option for its neighbors. That's forward checking. With every single choice, we're shrinking the problem and making it easier to solve.
Forward checking is awesome, but it's a little short-sighted. It only looks one step ahead, right, to the immediate neighbors. So the obvious next question is, what if we could go further? What if we could create a domino effect that ripples through the entire puzzle?
And that brings us to something way more powerful, arc consistency. Okay, this sounds complicated, but stick with me. Imagine a constraint between two variables, x and y, as a one-way street. We call this an arc. For that arc to be consistent, it has to follow one rule. For every single value in x's domain, there has to be at least one value in y's domain that doesn't break the rule. So, if you're looking at x and one of its options is blue, but you see that blue conflicts with every single remaining option for y, well, then blue is an impossible choice for x, right? So you can just delete it. When you run this check across the whole system after every single move, which we call MAC for maintaining arc consistency, you get that domino effect we were talking about. It's an incredible way to find those hidden dead ends.
But wait, there's more. We can push this even further. There are some really advanced tricks we can use to make our algorithm not just smart, but to make it actually learn from its mistakes.
You see, normal backtracking is kind of dumb. When it fails, it just takes one step back. But what if the mistake was made 10 steps ago? Back jumping is way smarter. It figures out the real source of the problem and jumps all the way back to that specific decision, skipping all the useless stuff in between. Then there's constraint learning, which is just amazing. It's like the algorithm literally takes notes. When it fails, it records the exact reason why it failed and adds that as a new constraint, a new rule. That way, it guarantees it will never make that same stupid mistake again. These two techniques can take a solver that's crawling and turn it into a lightning-fast problem-solving machine.
Okay, we have covered a ton of ground. Let's hit pause and pull everything together. We're going to shift gears now and focus on exactly what you need to know for your exams. This is the important stuff.
Here's your checklist. Number 1, you have to know the 3 pillars of a CSP, inside and out: variables, domains, and constraints. Got it? Good. Number 2, you should be able to take a small problem and walk through the backtracking steps, using MRV to pick your next variable and forward checking to cross off possibilities. 3, make sure you can explain the difference between forward checking, which is just a one-step peek ahead, and arc consistency, which creates that big ripple effect. And last but not least, never forget the philosophy behind MRV. Fail first. The whole game is about finding problems as fast as humanly or algorithmically possible.
So there you have it. We've basically built a really smart problem-solving engine from scratch, starting with simple puzzles and ending with a framework that can tackle huge, complex challenges. So I'll leave you with a question to chew on. Now that you know how this works, what's the most massive, complicated, real-world scheduling or logistics problem you can think of that a CSP could solve? I mean, think about airline schedules, factory production lines, university timetables. The possibilities are just massive. Thanks for tuning in.